P2p applications. To be honest, this is one of my favorite sections in Chapter 2. Alright, so P2p architecture. As opposed to the very simplistic client-server architecture where we have always-on service, in P2p, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. Okay. And the IP addresses to establish physical connectivity can also change over time. Right? So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent. Okay. And the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. Right, there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Right? Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. So the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. So server is over here, the uplink capacity is US. Well, therefore the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting. Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here will need to upload the copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US. And to send N copies altogether, NF over US. And this is the term that we have here. Because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. The client carrying the minimum download rate, let's assume the value is d mean. Therefore, the download time is F over d mean. The smaller the d mean is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over d mean. That's considered an N that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with N increasing? Well, this term suggests the overall distribution time will increase linearly in N, okay? While the minimum bandwidth for downlink might not change all that much. Okay, so potentially the overall delay, if we change N, is growing like this. Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Right? Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over D min, which we explained. And clients overall as aggregated system, okay, must download NF bits, okay, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. All right. So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If we want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, okay, over the entire capacity, entire uplink capacity of the system. Right? So the distribution time bounded by one of these three terms. All right, now consider again if n is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n? Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this. Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time. Right? So the scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, F over U, and let's say that that's 1 hour. And the server uplink rate is 10U, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10U. Therefore, what? F over U. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall. All right. And what is the total uplink capacity of the system? So user has 10U. Each client has what? 1U. So 10 of them, also 10U. Altogether, 20U. And how much is this? Half of F over U. And this is what? Half an hour. And is that right? It is right, right? In P2P's case, 10 users, only half an hour. Okay, so you see the growing trend, linear in client-server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. All right, and this is the big advantage of running an internet service in the P2P architecture over the client-server